tranquilo, é só ligar o microfone.
Tá transmitindo?
gives you a max value when P entails C, at least if it's non-paradoxical. I'll come back to that. And a minimum value if P refutes C. Again, non-paradoxical. So we're setting aside the paradoxes of intent for now. We'll come back to those later. And then values in between. And for Sturm's, he doesn't believe that there's a single function such that for all arguments, so he rejects that like I do. He also doesn't think that the function is a priori. So he agrees with me about that too. He has a much more subjective interpretation of the function. We'll get to that later. I'm not going to do that in general, maybe in some applications, but I'm not going to do that in general. But anyway, here's what he's going for. And now he considers a proposal. Let's call this proposal number 1. Here's proposal number 1. The strength of an argument from P to C, he says on the first proposal, is the probability that the conditional, the material conditional, corresponding to the argument. It just corresponds to this probability. So the higher this is, right? Now, this is a very natural idea because after all, we know this from logic, of course, that this argument is valid if and only if the conditional is a necessary truth. And here we mean logically necessary, but that doesn't matter. So here's a very natural idea. If you want to talk about strength, you do this. And here, it's strong according to always according to a probability. I'm going to stop writing that. Okay? My relation is a 3-place relation. It's a relation between a premise, conclusion, and a probability distribution. Okay? And for Sturm's too. So you see what's happening here? This argument's valid if and only if this conditional is a necessary truth. Oh, here's a generalization, just required to be probable. Very natural. Terrible idea. Terrible idea. Why? Consider the following argument. X, therefore, it is not the case that X. And here, X is just some contingent claim. Okay, it's nothing fancy. It has an intermediate probability, let's suppose. It's just contingent. Okay, it's an empirical thing. So according to proposal 1, so let's call this S1, because it's proposal 1. So according to S1, the strength of this argument, which we write this way, not X, X, is what? It's the probability of the conditional. Okay, but what is that? That's just the probability of either not X or not X by propositional calculus. That's just the probability of not X. Oh my gosh. So if X is improbable, this argument is arbitrarily strong. Just crank the probability of not X high, and now this argument is strong. That's absurd. This is a refutation. And so you see, this proposal violates this desiderata. So it's out. Do you see what's happening? It's out. It's a nice idea to start with, but it doesn't work because it fails to generalize the refutation case. It does do good on the entailment case, right? Because if the argument is valid, then this will be a tautology and it'll have probability 1, and that's max on the scale. You see what's okay? Do you understand what's happening? Okay. So this is out. Nice idea, doesn't work. This refutes it. Does everyone understand why this is a counterexample to proposal 1? This argument should be weak a priori. It's a refutation. It's a tautological refutation. It should be weak a priori. But it's not, because if it's improbable, if X is improbable, then this is a strong argument. And that's absurd. From the point of view of inductive logic, understood as a generalization of the non-paradoxical intents, which I'm accepting. I accept that with Garnet. That I accept, and so does Sturm's. Okay? Does everyone follow? Okay, so this is gone. This proposal won't work. Nice idea. Doesn't work. Okay, so Skirms then says, all right, well, here's another proposal. Let's call it proposal 2. And he says this, let's try this. The strength of an argument, according to a probability distribution, is just the conditional probability of the conclusion given the premise. In fact, this is what Carnap would have liked this. This is kind of Carnap's idea. Okay, well, this definitely does much better on this desideratum, because as long as this is not a paradoxical case and it's not a case with extreme probabilities, then what we're going to get is that this is going to equal 1 if P, tautological, if P entails C, and it'll equal 0 if P refutes C. Again, except in extreme cases, but let's set those aside. Let's not worry about the extreme cases. Does everyone see what's happening here? You just apply the definition of conditional probability. And of course, if you have an intent, this is going to be 1. If you have a refutation, it'll be 0. Except for the extreme cases, but let's set those aside. Now, we'll worry about the paradoxical cases later. So this is definitely better, much better. So now it gets this thing, it gets this desideratum right. And this is the theory Skirms accepts. Now I haven't told you about what the probability function is that Skirms likes. He still likes there to be 1. But for Skirms, it's the rational credences of the agent who's evaluating the argument. The credences that would be rational for the agent who's evaluating the argument to have. This is wrong. Sometimes that's right. Sometimes that's the right probability function, but not always. So I disagree with Skirms. Okay, so you might think, we're done. And in fact, the traditional theory of inductive logic stops here. There's disagreements about what probability functions are suitable. We'll get into that later. But formally, this is what all the inductive logicians going back to W. Johnson and John Maynard Keynes and Carnap. But this is wrong. And this is where the second dimension comes in. This would be a one-dimensional theory. It's just conditional probability. That's it. But it's not right. And on the handout, I give this argument. It's a famous argument from philosophy of science called the Fred-Fox argument. Okay, here's an argument. Fred Fox, who's a male, human, has been taking a rigorous regimen of birth control pills for many months. Therefore, Fred Fox is not currently pregnant. Okay, well, what's the probability of this argument? Intuitively, what's the condition? How probable is it that Fred's not pregnant, given that he's been on a rigorous regimen of birth control pills for many months?
1.
Not necessarily, let's not say 1, but it's definitely above any threshold you want to pick. Okay, it's high. So according to Skirms, this is a strong argument. This is not a strong argument. The premise provides no reason for a suitably informed evaluator to believe the conclusion. And what do I mean? I mean, to be more precise, here's what I mean. I mean this. The probability of the conclusion given the premise is just equal to the unconditional probability of the conclusion. In other words, the premise is irrelevant to the conclusion. And I claim strong arguments are relevant arguments. Why? Because the explicandum that I'm interested in is some things being a reason to believe another thing for a suitably informed agent. That's not happening here. So this is not a strong argument in the sense that I'm interested in. So that is what I'm calling, on page 6, strong arguments are positively relevant. In other words, if an argument's strong, then its premise raises the probability of this conclusion for a suitable probability distribution that we think is appropriate to the evaluation of the argument. Now, that's where all the action is in the modeling. How do you come up with the probability? We're going to get to that in applications, but let's just take this intuitive case, and I think we can all agree that in the intended sense, this is not a strong argument. Does that make sense? Does everyone understand what I'm doing here? Does everyone see why in the intended sense, this is not a strong argument? Okay, so what we have are two dimensions. And this is why that dream of a single function, no matter what probability distribution, whether you're a pluralist about that or whatever, it doesn't matter. It's still wrong. Because there's two dimensions. We have two dimensions here. We have the probability of the argument. That's the Stearns thing or the Carnap thing. That is relevant. That's an important dimension. We have that. I do agree that that's an important dimension of assessment, yes. It's not the only one. We have another one here. You're going to see a lot of these four-quadrant diagrams now. And what we have here is three regions so far where we have irrelevance here. This is the irrelevance point. Okay. I'm putting it halfway. This is negative relevance down here. So down here we're going to have a less than, and up here we're going to have a greater than. And so now, if we were to plot on our diagram here, intuitively, where the strength of this argument, the threat class argument, lies, where do you think it lies? If I want to put a dot for this argument, so here's, if I want to put a dot, where do I put it? Well, no, but I can be more specific.
The point?
It's going to be near here. Why? Well, because it's going to have high probability, but it's going to have zero. This is the 0 point. Zero relevance. It's irrelevant. It's not positively relevant, and it's not negatively relevant. So it's on the midpoint. See what's happening? Okay. And where we're going to go with this eventually is we're not done. This is part of the way there of where we want to get to. It's not all the way there because it'd be nice to have a quantitative measure here. Because this is, it's still very qualitative. So what you have, these are going to be the strong arguments. These are definitely going to be weak. And then there's what I'm going to call mixed arguments. And we can already see this is happening, right? We already see that if you're up here, then your high probability and relevance, I'm going to call those the strong arguments. Here you have low probability and negative relevance, or irrelevance. That's clearly weak. And here's where the tricky cases reside. What happens if you have an improbable but highly relevant argument, or a probable but irrelevant argument, like this one, like the Fed Fox argument? How is the argument strong? I'm going to say no. How strong is it? I don't think that question has a definite, determinate numerical answer. I just don't think there's an answer. It depends. It depends on, in the context, whether probability is more important or relevance is more important. And in some contexts, probability may be more important for the assessment, but in another context, relevance may be more important. And I want to say, well, those are incommensurable values in general. They're incommensurable dimensions of assessment. And so there just is no fact of the matter about what the degree of strength. There is no single scale. There's no total ordering. Now, there's things you can say, of course. Once we have a quantitative measure here, which we'll do later today, once we have a quantitative measure, there's things you can say. So for instance, suppose you're here and you move up this way. Now you've gotten stronger because you've got stronger unanimously in both dimensions. Or if you're here, say, and you move this way, well then you've gotten weaker. So there's things you can say. There's a partial ordering. There's a partial ordering, but there won't be a general and total ordering. And that's okay. The dream was a total numerical ordering. Not going to happen.
You can measure by the derivative, right?
You
in a
could,
certain sense.
yes, that's right. You could say if there's a positive
Yeah.
change,
Yeah.
then in both directions, then you've gotten stronger.
Yeah.
Sure, and we can. That's fine. I'm happy with that. But there'll be cases. What happens if you go like this? So you start here, and then you go like this. Have you gotten stronger? In a sense, you have. You've gotten more relevant, but you've gotten less probable. I just want to say there's no fact of the matter about whether you've gotten stronger since literature. Not in general. Maybe in some cases there is, but not in general. This is where the two-dimensionality comes in. It's a very important difference. So there's all this stuff about there being a single function. That was wrong. That for all arguments, there was the quantifier problem. That, okay. But then there was the fact that everyone's assuming a single dimension, but that ignores relevance. That's wrong. Okay. So there's two dimensions. Okay. Now, let me actually write down the qualitative definition of strength that I'm going to adopt here. So according to my theory, an argument is strong. And of course, I mean according to an evaluative probability function, probability model. Strong according to a model. It's always according to a model. This is where modeling comes in. It's modeling. Remember, this is not a priori. Sometimes it is, but generally it's not. What does this mean? This means this. If and only if two things hold. One, the argument is probable. And two, the argument is relevant. So we have two dimensions. We have the probability of the argument, and that's what Carnap and Stearns and Keynes and all those guys, they thought that was the end of the story. It's not the end of the story. It also needs to be relevant. Because if it isn't, then it's no reason to believe the conclusion at all. And therefore, in the sense that I care about, it's not a strong argument. Does this make sense? Does everyone understand what's happening here? Yes.
In what sense can you say that when you capture the second dimension, the relevance dimension, you can capture the causal direction? Because
Yes.
when you have this kind of argument, this is a very famous example of a refutation of Handel's
Yeah.
deductive nomologic example, because it can't capture the relevance
That's right.
aspect.
Yes.
Because it's based on the normal deductive logic.
Yes.
But when you put probabilistic into it, you can capture some relevance,
That's right.
but you can't capture causal direction. An explanation arguments, like because and so on.
Good.
In what sense can we solve this problem here?
That's
if we can.
Oh, I think we can. So that's a great question. That's a great question. And so now, what this is getting to on Friday when we talk about applications, I want you to raise this again. But let me just say a little something now. Remember, all these assessments are relative to a model. There are lots of different kinds of probability models in the universe. Among those are causal Bayesian networks. We can use those.
Distinguish cause and effect.
We can use those if we like. Of course we can. Because remember, and maybe we'll spend more time on this on Friday, but for instance, for those of you not familiar with Bayes nets, they're just a way of specifying a certain kind of probability distribution over a certain set of variables. So you might have something like this. You might have P as a node in some network connected to some other stuff. Right. And then maybe the conclusion is another node. It can be. And because P, and let's just make it simple. Let's just make these atomic sentences, okay, in the language, right? That's fine. Because remember, the Bayes networks, those are just discrete models, so they're just atomic sentences for the nodes, in our sense. But we can interpret these however we like. So if we want not just the strength in my sense, so I'm just talking about strength in a weaker sense than what you're talking about, but we can capture the stronger sense because instead of looking at P, we can look at this. We can interpret that atomic sense as actually do P, as an intervention on the premise variable in the network. And by doing that, and now if we apply our measure of strength to that interpretation, we'll have not just a measure of how strong the argument is in my sense, in the inductive sense, but we'll have a measure of how strong this is as a causally relevant factor. So we can certainly do that. That's just another way of writing down models of my theory.
So causal direction is not a third dimension.
No, because you can capture it.
You don't need to do that.
You can capture it. The key is allowing this atomic sentence to be interpreted as an intervention on that variable. And remember, we can interpret our atomic sentences however the hell we need to. That's the point of modeling. Okay? So we can certainly do that, and maybe we can address some real examples, just to illustrate it on Friday if we have time. But does that make sense? Do you see what I'm doing? We have a fully general model. Any discrete probability model can be captured in our framework. Any. That includes ones that are specified by base nets.
Continuous models, even continuous models, why not continuous?
Well, there's a sense in which, not generally, because, okay, there's a sense, yeah, this is good, and I wish Julia was here, but anyway, yes, yeah, of course, we're going to be able to capture certain aspects of what happens in continuous probability models, but we're not going to be able, in our framework, to give the kind of general models that someone like Professor Stern would want. Because there, he really wants an uncountable set of hypotheses. We can't do that.
Yeah, we can, sorry, okay, but we can sort of use a continuous measure and get a sort of finite or discrete subset of events.
Yes, sure. We can discretize.
Yeah.
We can also interpret extra systematically the hypothesis as being in a continuous space. But what we won't be able to do is explicitly represent all the alternative hypotheses.
Right.
Okay, that's a limitation of the model as I've set it up. However, if you want to do that, you can generalize this model just by generalizing the theory of conditional probability that we're using. Because you have to allow it to have probability 0.
Then we use a likelihood or measure like that.
Well, no, you just need a more general theory of this. If you have a theory of this for when this has probability 0, then yeah, you could plug it in and you could model things. We don't have that, okay? So we're, in my theory, it's a simpler theory. It could be generalized, sure. You could generalize it, but I'm not going to worry about those cases. I'm going to set aside infinite cases. You know, a more sophisticated version of the theory would handle those, but I'm not going to worry about it. But does this make sense in answer to your question? Because we can represent any discrete probability model in our framework, just with suitable interpretation of the atomic sentences. Of course we can represent base nets and causal base nets. No problem. Those are just ways of specifying distributions over claims that are, some of which are interpreted as interventions on the variables. Okay? And then the rest of it is just a recipe for calculating the probabilities. That's fine. Then that gives you different probability models. We can represent that. We can do all that stuff. That will just be a class of models within our class of models. Do you see what I mean? I'm trying to impress upon you how general what we're doing is. It's extremely general. But that means we have to be careful. Because if we're going to do this, we need to make sure that this is inadequate to the causal structure of the problem. If that's what's relevant to the strength of the argument, that's okay. That's called science. Inductive logic is a branch of science. It's not a priori.
At the end of the day, you have to put insert the data, the statistic,
Yes,
data.
you're going to have to do science,
The model,
statistics.
you can extract from the model. You have to
Absolutely.
insert this value from the model.
Absolutely.
We have to know what's cause and effect.
Or we have to have a model of it that we can represent among our class of models. And we have to be careful when we do that because we're going to have to put in the right extra systematic constraints to capture what we think is true of the system we're modeling in the world.
Okay.
But that's how science works, period. There's nothing special here. We're just doing science. It's a part of science. It's a branch of science. Does that make sense? In answer to your question? It's a good time to take other questions. Yes?
I was thinking about this case where we have this irrelevant x.
Yeah.
Okay. Imagine I have the following scenario. I am studying, and I think Q that B that I have B, therefore Q. Okay. However, studying further, I come to conclusion that Q is a tautology, so it would be true anyways.
Yep.
Couldn't that be considered an addition to my knowledge that something that previously I didn't know was a tautology, and now I know is a tautology?
Good. This is a very deep question. How much time do I have?
We're going to talk about that, but we're not sure.
We started 15 minutes late.
Okay, so we have like 10-ish minutes.
Let's do 11.
Okay, let's do this. This really should happen in chapter 5, but I think we've covered everything I wanted to cover, so is that okay? I'm going to address this question. There's two parts to the question. One is relatively simple, the other is much deeper and requires a lot more care philosophically. Here's the easy part of the question. Suppose you just have this paradox of entailment, and we're going to talk about this more on Friday. Remember this paradox of entailment. P therefore either Q or not Q. Is this strong? No. This is going to be a weak argument on our theory, as it should be. Why? Well, because of this. And here I'm assuming P is contingent and it's no extreme probability. It's okay. Let's not fuss. This argument is irrelevant. And that was exactly the complaint of the relevance logicians, because there's no variable sharing. Variable sharing is a very poor way to think about relevance in science. This is a much better way. Does everyone understand what's happening? Now, but that wasn't your question. That was related to your question, but you have a deeper question, but I want to first point this out. We'll come back to this on Friday, but you have a deeper question in mind. And I do want to talk about that a little bit here, since we have time. Your question is about logical learning. This is a very difficult question, but it's answerable in our framework. Certain aspects of it are answerable. It's not fully answerable, but that's okay. That's going to be true of any model of this type, any class of models of this type. Here's a version of this that is answerable. Suppose what we're talking about is a case where okay, we're not going to be able to do Q or not Q. Okay, that we won't be able to do. But let's take a different kind of necessary truth. Okay, so actually, let me just do it this way. I'm going to just call H to claim that all rigors are flat. And this isn't meant to be a sophisticated case. I'm just giving it as an example. Obviously, to make this interesting, it'd have to be a much more interesting entailment that wasn't so obvious, but just run with me. It doesn't matter. Now take the argument that argument is not tautologically valid. This is good. This is a feature of our system because it's going to allow us to model logical learning in this case. So as far as our theory is concerned, the probability of B given H and R can be intermediate. I could assign it the value 1, but I could assign it the value 1/2 just as well. That's a perfectly legitimate thing to do in our framework. And now what would be the motivation for this? Again, forget that this is an obvious entailment. Okay, that's not important. Suppose it was some complicated theorem of number theory. Okay, doesn't matter. That's not the issue here. If we want to model logical learning, we can do it. We can't model learning of tautological entailments because those are baked into the probability models. But we can model learning of higher order relations or mathematical relations. No problem. Suppose our agent, they're very bad at monadic predicate logic. They don't antecedently recognize that this entails this. But then they learn E. And E is the higher order entailment. And now I mean in predicate logic, not tautological entailment, in predicate logic. We can interpret it this way. We can interpret it however we want. As long as it's not tautological, it won't be baked into the model. Do you understand what I'm doing? Okay. And now we can just write down a model in which and now we have a model of the learning event. It's a perfectly good model in our framework. This approach to logical learning is due to a person named Daniel Garber. He wrote a beautiful paper in 1980 about logical omniscience and the old evidence problem. You can just look up Garber and old evidence, and you'll find it. It's a beautiful paper. And Garber basically sets up a framework just like ours, where we use atomic sentences and a truth functional background language, but we're allowed to interpret the atoms as involving higher order or first order entailments. And so we're allowed to learn those. And now we can model the learning event. What's learned is this. Okay, this person's really bad at logic. That's not the point. It could be a theorem in number theory that's very hard to prove. Who cares? That is besides the point. It's not the issue. Do you understand what I'm doing? You understand what's happening? Okay. This can be done. There are limits. This is good because it brings up limits. Remember, every class of model has limits. For every class of models of any scientific theory, there are cases outside the scope of its domain of explanation. That's true of my theory. This isn't outside the scope. What would be outside the scope is, could we model someone who learns this? No, we can't. Because those are baked into the model as having probability 1, and therefore nothing is relevant to them by the probability calculus. This is fine. Why? Every class of models has limits. Here we bumped up against one of the limits of our models. But there's another sense in which it isn't limited. As long as the logical relations we're talking about aren't tautological in the model, we can model the event of learning that. You understand what's happening? This is very important. This is a wonderful paper. This really revolutionized, I think, the way people think about inductive logic. Revolutionized it because it allowed you to model logical learning in a Bayesian framework. Not all episodes of logical learning, because you can't model the learning of tautologies in the model, because that's baked into the model. But that's fine. So if you think about the models of Newton's theory, they're able to explain and predict lots of stuff, but one thing they can't is the motion of Mercury. The planet Mercury and its motion is beyond the scope of the models of Newton's theory. And that's to be expected since every class of models has limits in science. Do you understand what's happening? This is not a criticism of my framework. It's just a specification of some of the limitations that it has for modeling certain learning events. And it's a good point, but it's no more a criticism of my theory than it is a criticism of Newton's theory that it doesn't predict the motion of Mercury. Do you see what I'm getting at?
Yeah, I was thinking about it because when I saw this x and this axis of
Yes.
relevance, I was thinking, well, what if I add a temporal dimension with I didn't know was a tautology, now I know the tautology, or I had a conjecture, and now I know this conjecture is true or it's false, and well, I've learned something new.
Yeah. Okay, we have to be careful here. I'm not modeling learning. What I'm modeling is the strength of arguments. These are synchronic assessments. They're timeless assessments according to a certain probability model that we think is suitable for the modeling of the strength of that argument. And what you point out rightly and importantly is there's no model in my framework that would explain why this argument is strong. It can never be strong. And that is a limitation because you might think, what about this argument that involves a different kind of entailment? I can model this one. This could be strong in our framework because the probability can go from 1/2 to 1. No problem there. That's totally compatible with our models. Yes, and what we've come up against is a limitation of our class of models. We can't model the learning of tautologies in truth functional logic, but we can model the strength of arguments that involve higher order or first order entailments, or mathematical entailments, whatever you like. That's all well and good, and that was an innovation of Dan Garber. It was actually Garber's paper that inspired me to create a framework where you allow to interpret the atomic senses however you like. Now that's not going to help here because no matter how you interpret Q, this is going to have probably one in our models. That's okay. That's okay. So what we can't model is the learning of a truth functional tautology. But we can model the learning or the strength of an argument in first order logic. That makes sense? Do you see what's happening here? This is like the Bachelor argument from the point of view of our models because these are just atomic sentences. There's no variables here, so of course there's no systematic deductive logical relation, but we can model an extra systematic relation. So another way to put this is, we can't model this systematic tautology being the conclusion of a strong argument, but we can model other valid arguments as strong arguments. And even if they're tautological, so I haven't actually done your example yet, so let me do your example. I don't even really care if it's a tautology. Let's just say it's a necessary truth. Suppose someone learns Leibniz's law. Suppose somebody learns Leibniz's law, or some version of Leibniz's law. That's no problem. We can learn that. We can learn that. Okay, that's a logical truth in a sense, or it's good enough. It's a necessary truth. Okay, so just take the argument, and now we can model that. Just call this P, and call this P, and call this Q, or call this C. No problem. We can absolutely model this, and now it's going to depend on. If what we want to understand is that learning event, then what I would say is the appropriate probability function to use here is the rational credence of the agent before they learn the logical relation. Does that make sense? That's what Garber does. And I think that's the appropriate probability function in this case. Do you see how we're doing? This is modeling. That's what we're doing. We're modeling. Yes?
I totally get the Fred Fox example. I was just wondering if it's not a move that, for example, an advocate of the Skirm's second proposal would answer these kind of counter-examples, saying, for example, that is not a strong argument because it's a contingent fact of the world that we know that humans don't get pregnant. But there is something that it's about the probabilistic model beneath the question. It's not supposed to be modeled in the first place. I don't know if you get my...
Oh no, Skirms doesn't want to say that because of course he wants to model the strength of arguments and statistics, which are all contingent, which all depend on contingent knowledge. No, he definitely don't want to say that. That would rule out most of the applications of probabilistic reasoning.
Okay.
Yeah, you definitely don't want to do that. Yeah, 5 minutes. Yeah, another question.
Could you briefly elaborate about why isn't it possible to give two functions such that for every pair of premise and conclusion. You can. It is true that the argument that goes from the premise to the conclusion is strong if and only if both the values of the functions are high, because it's
That I think you
clear
can do.
the-
That's what I'm proposing. That's the theory I'm proposing. You can't. That's what I think you can do. That's what I'm offering as a theory. What you can't do is have a single numerical measure on a single scale of how strong the argument is simplicative. That's what you can't do. But yes, what we're going to see, and after the break, what we're going to is there a break or do I just keep going?
Yeah. 15-minute break.
Okay, so after the break, here's what we're going to do. We're not done because what we have so far is just this qualitative thing. We just have positive relevance, irrelevance, negative relevance, right? We have a numerical x-axis, but we have a qualitative three category y-axis. What we want and what we're going to get, take a little work, is a precise numerical measure of the y-axis. We will get that. And then here's what's going to happen. For every argument, well, okay, not every argument, we already saw, there's limits, but okay. For every argument in the intended domain of explanation of the theory of inductive strength that I'm on, there will, and for any probability function that's suitable, okay, we're going to have a pair of functions definable with the probability function, that one of which gives you the x value and one of which gives you the y value. So we're going to be able to, for any probability model that's suitable and any argument, we're going to be able to represent the strength of an argument as a vector of two real numbers. That's where we're going. But that's, I think, the best you can do. And a vector is not on a single scale. It's got two dimensions. They will not be independent dimensions, by the way. They'll be non-linearly related. It's a very complicated space. But they will be logically and conceptually independent. Yes?
But my question was
Oh, yes.
about the quantifier order in Carnap's desiderata for the function.
Oh, well, yeah, no, there certainly can't be a single function that will work for all arguments. Because it's a contingent matter whether one sentence is, say, probabilistically relevant to another. That's not a theorem of probability calculus, you see. And so there'll be some probability models where something is relevant and some where it isn't. So if your aim is to model an argument that is relevant, there won't be a single function because some arguments are relevant and some are irrelevant. So if there's a single function, for every single function, P is either relevant or irrelevant. You see what I'm saying? It can't be both, so there can't be a single function. Yeah. There can't be a single function for all arguments. Now, there might be probability models you can write down that are explanatory for a wide range of arguments. Sure, that's just a contingent thing though. Just like in any other model, like in Newton's theory, there's a class of models that's very useful for like predicting what all the planets do. But there's no single Newtonian model that allows you to explain every phenomenon in the domain of the theory. Of course, yes. Time's up, thank you very much.
mais da ele parou
Okay. Maíra?
So, it's everyone being here again, and we are going to continue the second part of today's tutorial of Professor Rodrigo Ferguson. He's going to continue on the historical inductive report.
Thank you so much. All right. So here's where we left off. We've got this kind of story where we've got a measure of how probable the argument is. That's just conditional probability. And then we have these three regions: positive relevance, negative relevance, and irrelevance. Okay, but that's all we have. What we want is a numerical measure here, so that we can have, for any probability distribution and any argument, any triple like that, we'll have a vector of real numbers. And this, I believe, will be as far as we can go for the numerical model. So for this, I need to discuss measurement and the nature of measurement. So I'll get to measuring relevance in a bit, but let's just think about how measurement works more generally. Let's take the case of temperature. So we can think of three kinds of measurement, three grades of measurement. And this is just in general, measuring any quantity, anything. Let's start with at the quantitative level, because that's where we want to go. And let's talk about temperature. So what we would like, and O is an object. So we want some measure of the temperature of an object. O could be like a steak. I like cooking steaks. And sometimes you gotta measure how warm they are. You don't have to, but it helps. So we have claims like this at the quantitative level, right? This is like the temperature is equal to X for some number, okay? And I'll assume those are real numbers on some scale. Now, if we have a measure like this, we're also going to have qualitative claims. And you can interpret that as the claim that the object O is warm. Y is just some threshold on the scale, and if it's above that threshold, we say the object is warm. And if it's below a certain threshold, we say it's cold. Okay, so up here you have like warm, cold, things like that, qualitative characterizations of temperature. Here you have a precise number, some real number X. To me, the most interesting level here is the middle level, is the comparative. Here you have claims like this. The temperature of object 1 is at least as great as the temperature of object 2. To me, this is the fundamental level of measurement. Okay, and now, let's take the case of temperature. There are many numerical scales on which temperature can be measured. There's the Fahrenheit temperature of an object. There's the Celsius temperature of an object. So suppose this is 0. Then what's this?
F was a Fahrenheit.
Yeah, Fahrenheit Celsius.
32. No, 32.
These are different numbers. Does that matter?
No.
No. These objects have the same temperature. This object, if we had two objects, intuitively, they have the same temperature.
Yeah.
The numbers are different. So measurement is not about numbers. What's important is this. The reason these are both measures of temperature is because we have the following fact. is what I will call comparative equivalence of numerical measures. That is crucial. If two measures are not comparatively equivalent, they are not measuring the same thing. Everyone agree? This is really important. In fact, we can say more about this. We can make a stronger claim in this case because it turns out that F equals, does anyone know? There's a linear equation.
5 times C. No.
Tem que reduzir, peraí.
It's really weird. Okay. 5 times C minus 32, I remember. Something minus 32.
Divided by 9 at the end.
Let's ask you, GPT.
It's,
Yeah.
Celsius times 9 over 5 plus 32.
We have a linear relationship. I don't need anything that strong because all I really care about is this. But of course this entails this.
Yeah.
Because if you have a linear thing, then all that matters is that it's monotonically increasing. That's all I really care about because I just care about this. And this is monotonicity. It's like a kind of monotonicity. Okay. Now, okay, that's temperature.
Wait. C.
Wait, what happened?
I mean, to convert, in order to convert, you get minus 32 multiplied by 5 divided by 9.
We remember how to get in Celsius.
We
Oh, you want to go the other route?
We use the other way around.
Yeah, that follows from this. Okay, so I'm good. That follows. Okay. Okay. So what I really care about, and I think is the most fundamental property, is comparative equivalence. That's like non-negotiable. If two measures claim to be measuring the same quantity, whether it be length or temperature, it doesn't matter, but they're not comparatively equivalent, then they're not both measuring the same thing. They're actually measuring two different things, if they're measuring anything at all. Does everyone follow? That's really important. Okay. Now let's talk about relevance, probabilistic relevance. Let's just talk about positive relevance for now. Okay, and that just means the conditional probability of the conclusion given the premise is greater than 1. Now suppose we want to measure. There's lots of things we could do. So here, what I'm going to do is I have the qualitative claim, and over here I'm going to write down a quantitative claim. Here's one way to measure it. Just take the difference between the left and the right hand side. That's a perfectly good measure, and it has the following nice property. It's a positive number if you have positive relevance. It's a negative number if you have negative relevance, and it's 0 if you have irrelevance. Does everyone see that? Okay. So in fact, it's on a -1 to 1 scale. That's kind of nice. So what you have here is +1 is going to be max positive relevance. -1 is going to be max negative relevance. And 0 is going to be irrelevance. And you have values, of course, in between, as determined by the probability function. Remember, it's relative to a probability. Okay, but something very interesting happens when we're trying to measure this particular quantity. There are many equivalent ways of saying, qualitatively equivalent ways of saying, that P is positively relevant to C. Here's another way of saying it. These are equivalent, logically, given the theory. I mean, that's a nice exercise. Maybe call it exercise 12. Prove algebraically that these are equivalent. Not hard. Just write down the algebraic thing. You'll see it right away. It's not hard. Okay. But take my word for it. These are equivalent in the theory. But that suggests this many. You see? And that will also have this structure. It'll be +1 when you have maximum runs according to this measure, and so on. Do you see? Okay, but we're not done. There's many ways. Here's another way. Probabilistic relevance is symmetric. That's also provable. So another exercise, prove that all three of these are equivalent. That just means it's a symmetric relationship. Wow, that suggests you could take, why not take the difference between these? Well, I'm not going to do that. I'm going to do something a little different. And I'll explain what I'm doing in a second. So I'm going to use the notation equal dot for comparative equivalence between measures. This, it turns out, is comparatively equivalent to this simpler measure. That's another exercise. I'm not going to prove that, but that's a theorem of probability calculus. This is called the likelihood ratio. It's also called the Bayes factor. That's the word that Professor Stern used. There are a lot of names for it. I'm just going to call it L. And I take this version rather than this version because this is on -1 to 1, just like these two. And I want to have a common numerical scale. Okay? Okay. And there's other measures besides, but I won't bore you with that. I list another measure on the handout as well, which I call R. And R is motivated the same way, except R is equivalent, and what I wrote down as R on the handout is comparatively equivalent to the ratio of the posterior to the prior, rather than the difference. Okay, it's a little more complicated because we do this trick again where we do P given C minus the probability of P plus the probability of P given C plus the probability of P. And, sorry, no, C. Sorry, C given P. C given P. It's on the handout anyway. Okay, instead of taking the difference between the left and right hand sides of the inequality we started with, we can take the ratio. And that turns out to be these things are comparatively equivalent. Again, I'm not going to prove that, but it's easy to prove in the probability domains. So that's another exercise if you're interested. Now, when you look at this, you think, well, fine. I mean, okay, there's these measures. What's the problem? Problem is, none of them is equivalent to any of the others. So they're all measuring different things. So what do I mean? I mean, D is not equivalent to L. D is also not equivalent to R. D is not comparatively equivalent to S. S is not comparatively equivalent to R. S is not comparatively equivalent to L. L is not comparatively equivalent to R. Now, I'm not going to prove all these things, but if you look at the handout, at the model, very simple model, on the top of page 7, which I just used the probability table generator to generate. that model is sufficient to show the following three instances of what I'm saying here. So that model shows this, shows this, shows this. It shows all three of those things. So here's the model. You just have to do it without sentences. We have 32 over 64, and then we have 15 over 64, and then we have 3 over 64, and then the other one is just 1 minus the sum of those. Okay.
Brandon,
Yeah.
wouldn't it be 33 instead of 32?
Wait. Oh, 33. Sorry. Yeah, I misread that. Thank you. Thanks. Okay, so this is a nice exercise, and I'm not going to go through all of it, but I do want to just explain what the exercise is. I'm calling exercise 6. So no, sorry, exercise 5. So what this model shows, the following three things are true on this model. So this model suffices to establish all three of these non-equivalences. Do you see that? The reason is because they all disagree on the comparison. So according to D, the argument from y to x is stronger, which we could write this way, than the argument from x to y. In other words, y is more relevant to x than x is y. So quality reveals another interesting fact. Qualitative relevance is symmetric. Quantitative relevance is very much not symmetric, and this makes sense if you think about it. A hypothesis might entail a claim E, but E doesn't entail H, and in that case, the degrees better not be the same. This one, on the other hand, goes the other way. And this one just says they're equally strong. That shows that all three of these measures disagree with each other. In fact, it's a stronger claim. There's a single probability function such that they all disagree. I don't need that. I just need for each of these claims there exists some probability function. And for this, some probability. Actually, you can do all three of them in one swoop. And there's also models where you can show these things, but I'm going to show these things in a different way. Now, what about L? We have these. Those we can show in a much simpler way. And I will do that because it's L that we're going to be interested in ultimately. How do you prove this? Very simply. You just write down the definition of this measure, you translate it into algebra, you plug and chug, you'll get a number, and that number will be greater than this number, and so on. I'm not going to do it, but it's a good exercise to do. Okay. Now, this is really interesting. And in fact, this problem was the topic of my dissertation many years ago. And back then I called this the problem of measure sensitivity, or let's just call it the plurality of relevance measures. And this is unfortunate. I want to say a little bit about this, but it's a very important problem because if you look in the literature, in statistics for instance, but really in any area that uses probability and uses probabilistic relevance, which is most areas of statistics, you'll see these different measures being used for various purposes. But generally people don't point out that there's no such thing as a single measure of probabilistic relevance. These are all measuring different things. So what this means is that there's many kinds of probabilistic relevance from a quantitative perspective. Qualitatively, they're all equivalent. But when you start measuring degree of relevance, which is what we need for our theory, there's many different kinds of degree of relevance. And they're different quantities because they don't even agree on which arguments are stronger than which, that is, which are more relevant than which. So there can't be a single notion of relevance, okay, quantitatively. This is a real problem, and what I did in my dissertation back in those days was I surveyed a whole bunch of arguments in the literature that he's given. There's a lot. I just scratched the surface. And here I'm also scratching the surface of the number of measures. I think there's dozens of measures of relevance that have been proposed that are not equivalent to each other. I just picked 4, but there's dozens. And what I showed in my dissertation is there's all these arguments out there that use a particular one of these measures, but if you switch to another measure, the argument is no longer logically valid. That's a problem. Because what that means is you have to, if you're using a quantitative measure of relevance, whether it be like a correlation measure, whatever it is, doesn't matter. Correlation is just a kind of relevance. Yeah, so the correlation measure, what's that? Here's a correlation measure. Because it turns out that if these are equal, that's another way of saying P and C are independent. So if you just subtract this from this, then you get another measure of relevance. And guess what? It ain't equivalent to it. It's equivalent to some of these, but not others, okay? So this is like another measure of correlation. But anyway, there's lots of measures, okay? And they disagree. And not only do they disagree about which things are more relevant than which, in particular applications that are sensitive to that choice of measure. That's what my dissertation. Okay, now that's fine. That's fine. Okay, because remember, science, we're modeling. That's fine. But what you're going to need to do when you're dealing with degrees of relevance is you have to have some background argument that the type of relevance that's at issue is the one that your measure measures. Otherwise, the argument might as well be invalid because it depends on that choice. So you have to justify it. So our task here is to figure out how should we measure relevance. So we've got these measures, so I've got 4 of them here, but it doesn't really matter. There's many in the literature. So the question is, which relevance measure is relevant for our purposes? Or if you like, suitable to our present purposes. And we have to answer this question before we can proceed. Because if we want a single numerical scale, well, we're going to have to pick a measure. If we pick a measure, there are many different measures. What are we talking about? Okay, now, this is where we can go back to Carnap and Stearns and the original, and Keynes and all those guys, and go back to the original motivation for inductive logic. And remember, there was a motivation there, which was, if we have a measure of inductive strength, we want it to be a generalization of non-paradoxical entailment. What does that mean? It means, if you have entailment that's non-paradoxical, you should have a maximum value. If you have a refutation, you should have a minimum value. In fact, it should be a maximally negatively relevant value. Okay, so that suggests this desideratum. Whatever our relevance measure is, it should satisfy this desideratum. And I'm just going to assume for the convention that we're on -1 to 1 squared, but we can always rescale things. That's just a conventional choice. So here's what we want. All these measures are already scaled, okay? So we want +1 when P entails C non-paradoxically. Again, set aside the paradox of entailment. Okay. We want it to be 0 when P is irrelevant to C. we want it to be minus 1 when P refutes C non-paradoxically. And then we want this to be greater than 0 when we have positive elements, less than 0 when we have negative elements. Why? Because we're doing inductive logic. And inductive logic is meant to be a generalization of non-paradoxical intent. So, this is a very good desiderata for us, for what we're doing, which is evaluating the logical strength of an argument. Here's the good news. There's only one measure that satisfies this. Okay, why? Let's think about that. That's easy to verify. Let's take a look. Actually, we'll just do it here. Let's look at our 4 measures and then see what happens when we have entailments or reputations. Let's just do it. It's easy to do. Suppose P entails C. Then what's this? This is 1. So this thing in that case becomes 1 minus the probability of C, which is the probability of not C. That's bad, because it ain't max on the scale. So that measures out. How about this one? Oh, well this is going to basically give us something like 1 over the probability of C. That's no better, because that could be really low too. So that's out. How about this one? This is going to be 1 minus what? Oh, so that looks good. But what about refutation?
Entail C.
Yes.
So
C, but not C.
no, not C implies not B. So this is just going to be 1 minus the probability of C given not B, which could be very low. Just as out. Okay. This one. This is 1. This is 0. And now refutation. This is 0. Right? This will be 0. And then it'll be this divided by this, which is minus 1. Yep. So that works. So that's very nice. Yeah. So the good news is, out of all the measures in the literature, this is the only one that satisfies our requirement that we be generalizing non-paradoxical entailment with our measure. Our x-axis already does that. Our x-axis already does that. We also want our y-axis to do that. There are 2 dimensions of the strength of an argument according to our theory, but they should both be generalizations of entailment. Why? Because that's what inductive logic does. It generalizes entailment and refutation. Now, I want to say, that's a very specific purpose. Measuring the inductive logical strength of an argument. That's a very specific purpose, but that's our purpose. And so now, we can just use this measure. And that's what we're going to do. So now we're in a position where we can state the theory. Now we actually have the theory. So now the theory is this. The strength of an argument is given by, again, relative to, it's always relative to a probability model. Relative to a probability model, because everything's relative to a probability model, is given by the pair of real numbers probability is the x-axis. And now we just use L. And that is our theory. So how strong is an argument according to a probability distribution? That question does not have a single numerical answer in general. There'll be some cases in which it's obviously strong in both senses, so it'll joke. But generally, it's going to be an ordered pair. Okay, think of this as the x-axis, and this is the y-axis of our diagram. Now, we can actually draw the real diagram for the theory, the map of argument strength. So here's what it looks like now that we have it. Now we have a real picture of how the theory works. That's the theory. Where it's understood, and I'll draw this because this is 1/2. That's usually considered to be an important value for probability. More probable than not. Okay. And now, these are definitely going to be strong arguments on our qualitative definition. These will be weak. These will be weak also, but I'm going to call them mixed. They're not strong, okay, because they fail on one of the dimensions, but they succeed on the other one. So they are weak technically, but they're mixed. They're not as weak as these. These are unanimously weak in both dimensions. These are unanimously strong in both dimensions. Here, these are strong in one dimension, like this case, relevance, but weak in terms of probability. This is strong in terms of probability, weak in terms of relevance. That make sense? And that's it. That's our theory. Pretty elegant theory, I think. Now, of course, when you want to apply the theory, now you're modeling. Because remember, the background here, this is all relative to this probability function. Very important. That's a parameter in the model. Well, there's actually 3 parameters in the model. Only 3 parameters in the model. Because we might as well just think of these as atomic sentences for all we can. We have 3 adjustable parameters in our theory. This is 1 minus this is the other. That's the theory. Now, models of the theory. Well, what are those? They involve 2 things. You want to specify a model. Here's what you need to do. You need to interpret P. You need to tell me what that is. What proposition does that express? What proposition does that express? In some underlying sentential language. Okay, fine, right? And then you need to specify a probability distribution, which just means you need to specify values for A1, A2, and A3 that are on 0, 1, and they sum to 1. That's what you need to do in your modeling. Now, underneath this might involve some atomic sentences here in the background. You have to specify those, and then these could be compounds, okay, whatever. But you have to tell me what the atomic sentences in the underlying language are, and that will tell you what these are, because these have to be definable in terms of those. They might be conjunction and so on. Doesn't matter, whatever they are. Yeah, is this making sense? It's actually a very simple model. It has 3 adjustable parameters, plus, of course, and this is the key, specifying the contents of the underlying language that are relevant to interpreting and evaluating the argument. So there's a lot of things you got to do, but that's all you got to do. Yes?
Yes, so you mentioned that there is no single measure of the strength of an argument, but since we have this pair with 2 places, you can define the pair of the strongest argument as 1, 1, and then you can calculate a geometric distance measure. That wouldn't be like an overall measure of the strain.
You could try to do that. Yeah, I mean, sure. And I encourage you to think about that. When we get to applications, we're gonna talk a lot about this. But yeah, I mean, if you think there's some function of x and y, I mean, you've got x and y here, right? Think of them that way. Then you could say, is there some function of x and y such that it's the numerical strength? I think the answer is no. Okay, but there's a lot of reasons why I think that. It's from using this theory to model lots of arguments, and it's a lot of experience with using the theory, and that's led me to a rather skeptical view about the prospects for such a single scale. But I'm open to proposals. I don't think they're going to work in general. I think there'll be, for any proposal, there'll be some very tricky cases where it looks like that ordering is very questionable. But we don't need a total ordering. I just want to say, there's no reason that we need a total ordering. We don't need a total. In fact, I think it's somewhat misleading to do a total ordering. When we get to applications, I'm going to talk about why. I think some of the explanations that this theory provides in real cases, like in cognitive science, for instance, that we're going to talk about, reasoning fallacies, that's going to be our main application. I think it's much better not to go for this. I think it actually reduces the explanatory power of the theory. So I don't want to do that. But I'm open to being wrong about that. Yes?
In general, inductive reasoning is no monotonic.
Yep.
But in case you have a strong entailment, a probable or relevant entailment, it is still non-monotonic in this system.
No, it's not.
It's monotonic, but only on the strong entailment. I think.
Yeah.
Okay.
Yeah. So let's think about it.
So we have an inductive reasoning, a model of inductive logic that has a monotonic characteristic.
Well, yeah, for the non-paradoxical entailments, it's going to be perfectly monotonic, just like logic is.
Okay.
That makes sense. That's what you want. It's a generalization of non-paradoxical entailment. Of course, it's going to say that the paradoxes are not strong. Okay, so that's jumping ahead to application. Let me not talk about that yet, but instead, let's do, and I'll take your question in a second, let's map two very simple arguments that we've kind of already seen. So here's an argument. What about our old friend x, therefore not x? Again, assuming x is contingent, has non-extreme probability, I'm not worried about the edge cases. Where does that go, the blue argument? Well, what's its probability? 0. And by the generalization of refutation constraint on L, where does L put it?
-1.
Yes, it's here. Which is what you want. This is the worst argument in the world. The end. Always, provided it doesn't have probability 0. Forget all that. Forget the edge cases. That's not interesting. Okay. Okay. What about this argument? X, therefore X. Same X, so it's contingent, doesn't have extreme probability. Where's it going to go? Up here. As it should. It's the best argument. From this point of view, where what we're doing is generalizing non-paradoxical entailments. See what's happening? Okay, now in between these, there's all kinds of possibilities. Let me take this question first, and then yes.
It seems to me that the way to delimit the area which represents strong arguments would also be part of the modeling process. Not only just establishing thresholds, but deciding whether you want to establish thresholds or other criteria for designating this area. Because I was thinking about like,
That's right.
You can do with this or this.
Absolutely.
If you're worried about the edge cases.
Absolutely right. You'll notice, look at by theory of strength. It doesn't say anything. Yeah, it just says the strength is the ordered pair. Yeah. Now, I'm tipping my hat to the old school, like Skirms and so on, because they thought that this halfway point is significant. Because when you're talking about a reason to believe something, it should make the conclusion more probable than not. This is traditional epistemology. You could reject that. You could say, no, I allow lower thresholds, like in science. Maybe all the alternatives are garbage, and I just want the best one. Okay, that's just moving the threshold. Not important. My official theory doesn't have thresholds. I was just giving a qualitative theory of strength and a tip of my hat to the old school and to the traditional epistemology. But I don't really care. I'm just saying the strength is the ordered pair. You decide what you want to say about that. That's fine with me. There is a technical point that has to be made here, which is non-trivial, that I want to talk about. And
Before-
yeah.
Whatever. Just a very quick question. What would relevant logicians think about this kind of measure? It's a beautiful measure, but what would they think about? Would they agree with that?
No, there's a fundamental disagreement that I have with relevant logicians, because they think that the way to fix the paradox of entailment is to impose a variable sharing criterion.
Yeah.
That is wrong.
Purely syntactic solution.
And it's wrong, because argument strength is not a matter of syntax, not even in number theory, because of the incompleteness thing. So forget about empirical examples. It's not even true in number theory. No, this is not a syntactic matter. I'm sorry. Okay, so I disagree with the relatives just because they want everything to be syntactically solved. This is the wrong approach. It's just wrong. So I disagree with that. I'm offering a different alternative. Now, there is a really important thing that I have to talk about here. How much time do I got?
30 minutes.
Oh, okay, great. We'll have plenty of time for discussion. But I do want to address a very important question, which probably occurred to you. See ya. Thanks. So, okay. Something that should occur to you immediately is, we've got these three parameters, and we've got these two, what I'm calling dimensions. This is somewhat misleading, because if you'll notice, you can just write down algebraically what the dimensions are. They're just functions of the three parameters. So what if we do that? So x is the probability of C given P, which is going to be A1 over what? A1 plus A2. We have to now go to the underlying algebra to really understand what's happening here. Okay? That's the x-axis. The y-axis is this measure L. What is that? It's the probability of P given C minus the probability of P given not C over the probability of P given C plus the probability of P given not C. What is that? It's A1 over A1 plus A2. Sorry. It's A1 over A1 plus A3. Right? Because it's C here in the denominator. Okay. Minus what? What's the probability of P given not C? What's the numerator?
A2.
A2, P and not C, good. And then not C, well that's just 1 minus A1 plus A3. Right? Because that's just, this is C, this is not it. And now we have this. Now you can notice something very important. These things are defined in a nonlinear way in terms of some underlying real parameters. And the relationship between them is very complicated. They are not linearly independent or anything like that. These are not like basis vectors in some vector space in the usual sense. They're not, that's not what's going on. So to call them dimensions is a little misleading. Okay, so what makes it okay to call things dimensions? Okay, this is would be a long story, but here's one thing that better be true. if this is going to make sense to call these like independent dimensions of something, then the following had better be true. It had better be true that what does this say? It says, just to put it in words, it says, suppose I pick a point inside. Let's not talk about the edges yet. The edges are going to be a different story. But let's just say we're not on the edges. We're on the inside. For every point on the inside, like suppose I come here, there ought to be a probability distribution that gets me to that strength. Turns out, this is not trivial to show, but it's a decidable theory, so we can just eliminate the quantifiers and verify it. It turns out, again, where these are non-extreme, it turns out this claim is true. For every non-extreme values of x and y, there is some probability distribution that gets you there. If that weren't true, it wouldn't make sense to call these dimensions. You see what I'm saying? If some of the regions were inaccessible, that'd be super weird, and we wouldn't want that. Turns out, not a problem. Not easy to show. This is a very difficult thing to show, but since the algebra is decidable, you can just use quantifier elimination to verify, which I've done. Now, what about the edges? Well, the edges are a different story. Right? Suppose the conditional probability takes the value 1. Well, then so's this. That's going to constrain this. It's going to prevent that from taking certain values. Okay, so on the borders, there's problematic cases. Not these. These are fine. But like, you might ask, what about this? Can't happen. And that's fine. I'm okay with that. Or this. Okay. So those are holes in this, but every other point is accessible by some probability. So this really is a map of all the possible strings. That's not an easy thing to show, but you can use quantifier elimination to verify it. I haven't actually seen a human readable proof of it. That's a nice exercise. If someone could prove this. I mean, it's just elementary algebra, really, but it's just a statement in the theory of real close fields.
Couldn't become common with
Well, can I plug in the computer? Okay. So this is a good application. I mean, I was going to talk about this on Friday, but I'll just talk about it now. We have time. So let me show you. You can verify this using Mathematica. Not using the probability table generator, because that's just for finding examples. You can't do mixed quantification like this. Okay, but you need the full theory of the reals, which allows arbitrary quantification over all real numbers. Yeah. So, so when that comes up, also I put in the exercise that was in the WhatsApp, just to show you that this is a decision. There's nothing numerical going on. So it actually calculates and gives you irrational values. Because it's a decision procedure. It gives you the exact answer. It's not a numerical thing. Okay. Anyway, but that's not what we're interested in. Let me go here. Yeah, no, that's okay. But I need to bring up the relevant file here. Where is it? Yes, there we go. There we go. Okay. So I'm just, instead of using A1, A2, and A3, I'm using A, B, and C. Okay? And I'm using X and Y for the variables. So now we have these two dimensions. Call them probability and relevance. And here's their algebraic representation, as we already wrote down. Claim. Okay, now I gotta unzoom this. Let's see.
Control minus.
Here's a claim in the theory of reals. For every way of assigning values to P and R, there exists a probability function. This just says it's a probability function. Okay. There's some constraints on it here. These can't. Some of these have to be greater than 0, such that this is true. And now you'll see this is false because of the edge cases. But now we can ask it to give necessary and sufficient conditions. Okay, this is going to take a bit. But it will eliminate the quantifiers and give necessary and sufficient conditions for when this holds. And you'll see, the only cases it doesn't hold, it's still calculated, but I have the old answer here. If the relevance is -1 and then P is here, that's ruled out. Okay? If P is 0 or P is 1 and this is true, then that's ruled out. Or R is 1. Okay, so it's all extreme cases. In the interior, this claim is true. And you can see that by now restricting it to quantifiers that put everything on the interior. And now you ask it, eliminate the quantifiers, and it just says true. Okay, that's no proof, but it's knowledge. And that's what I'm interested in. So this is a really important thing you have to establish. Now, I don't actually know of a human readable proof of this. I guess it's not going to be trivial, people. But I haven't even tried. Okay, but this establishes it. So I don't want you to take my word. This gives you the exact conditions. And so it's only on the edges where there can be conflicts. Which kind of makes sense. I mean, that makes sense because on the edges you have things like weird deductive combinations that shouldn't be compatible, right? Like maximally probable but minimally relevant. What does that mean? Or maximally relevant, minimally, that doesn't make any sense, okay? But other than that, as long as you're in the interior, it's possible, okay? And that's important because if there was some hole in the space because of the interaction of the two dimensions, it's really not good to call them dimensions of the same, right? That would be weird. So this is like a minimal requirement of making it okay to call them dimensions. Now, they're not linear bases. It's not a linear space. It's a highly nonlinear space. But you can actually visualize, and I won't do that right now, but maybe on Friday, you can just visualize things, because you only have 3 parameters. So you can visualize in a 3-dimensional way what all the combinations look like. You can just know that. That's determinate. That's like there's a decision procedure. So you just know. That's the beauty of this theory. It's not just decidable, but you can just calculate what the different regions actually look like as a function of the underlying parameters. There's only 3 parameters. It's a 3-dimensional space. It's a really weird nonlinear 3-dimensional space. It's not, but it is a 3-dimensional space in terms of A, B, and C. And it's okay to think of these 2 dimensions as dimensions because all the things are achievable. For every combination of strength, for every strength value, there's some probability distribution that will get you that strength. Okay, that's kind of important. I think if that wasn't true, you'd start to worry that these 2 dimensions are too dependent on each other. And that you're not really identifying 2 dimensions of something. Maybe it's less than 2 dimensions because if they were that dependent on each other. But they're not. Okay. How much
It's a Cartesian product. 2 linear spaces.
No, they're non-linear
No,
spaces.
it's a Cartesian product.
They're not linear spaces at all because this dimension is a ratio and that one's a ratio of sums of ratios. The underlying space is A, B, and C, but what X and Y are very complicated functions of the underlying 3-dimensional space. But they're independent in the sense that for every value there is a probability distribution that will get you there. So all these strengths are meaningful. They can all be achieved by some probability distribution. Okay. All right, questions? I can go back to the board. Friday we'll do more theorem proving and automated reasoning stuff. But because this theory is so simple, you can just calculate all the theoretical properties of it if you want. Yes?
Question, I don't know if I'm thinking right in what you're saying, but anyway, can we take an example of statistical clinical trial to try to fit your model? So, for example, we have a conclusion. Say you have a test, a very good clinical trial that the analysts would say it's the gold standard, and like for example for a drug to lower cholesterol. So this drug, the conclusion is that this drug is effective. But you have two premises. Suppose that the study is statistically significant, so it's very good study, but also you have the premise that the study is clinically insignificant. So let's say the studies you have the greatest is very possible. But say that this person, you measure that this person who takes the drugs will live only 5 days more than people who are not taking the drug. So it's insignificant because it doesn't matter if you're going to live only 5 days more or 1 week more.
Yeah, I think I understand what you're saying.
Can we measure the
Yeah.
relevance of these two?
So okay, good. So now we're getting into application. I might as well start now. We'll just, if that's okay. We'll continue on Friday with that. I have a bunch of applications I want to discuss, but this is good because it raises the question of application where you're actually modeling a real case. Let's think a little bit more generally. I don't want to talk about specific cases because we're going to get too much in the weeds of the epistemology of determining the strength value, and I don't want to get all caught up in that. So let's simplify things a little bit. There's in general, in science, and here now I'm talking about empirical science. In empirical science, what often happens is this. An experiment is designed to test a certain hypothesis. And then the experiment is performed. And so let's just take a simple example, which we'll come back to later, a simple kind of example. Let's let H be the thing that some person S is pregnant. So I'm going to start with a diagnostic testing case, but then I'm going to generalize that. And let E be S got a positive result. From, let's just call it pregnancy test T, which they purchased at their local pharmacy, I suppose. And now consider the argument. E, therefore, H. What we want to know is getting a positive test result, in this case, a reason to believe that one is pregnant? Well, not so easy to say. Now we're into the real blood and guts of modeling. Okay, now we're in the mud. This is not trivial. Nothing's trivial now. Okay, this is hard. So what can we say? Well, if you go to the pharmacy and you buy one of these tests, then generally there'll be some information on the box. Does anyone know what information is usually included on the box?
First of all, accuracy and efficacy of the test.
Something about the reliability of the test. More specifically, can anyone tell me what conditional probabilities do they give you?
Well, specificity and sensitivity. What's value for men?
No. They give you these probabilities. Yes, they give you the likelihood and the catch-all. Remember, that was the terminology from our use of Bayes theorem. Oh! Oh, look. That's just ordinally equivalent, comparatively equivalent to L. And so from our perspective, it is just telling us what L is. They tell you L. This is very interesting that this is true. It didn't have to be true. Remember, how did we get to L? From Carnot. From the idea that what we were interested in was the logical strength of an argument. And yet, here we are. And what we're reporting on the box is our y dimension. I don't think this is a coincidence. I think this is not a coincidence, okay? This is just our y-axis. And so, normally what happens is that this value, typically, if you buy a test in the store, does anyone know? It's typically greater than or equal to 0.8. Maybe it's better, but it's usually at least that good. Oh, well look. We know already we're up here. Well, that's nice. Can we say what the strength is? Ah, now is where things get difficult. This can just be determined in the laboratory. But if we want to know the posterior, which is our x-axis, what are we going to need to know? We're going to need, well, more than that. I mean, there's a quantity that we're missing. Not just a calculation, a quantity. We're going to need to know the prior. This is not something that can be determined in the laboratory. It depends on S's behavior, if you will. You understand? Yeah. You need to know more about S. So I say, you want to know how strong this argument is? Tell me a story about S. And make it detailed. Because I want to know. The end. That's the story. That's it. That's all there is to this. Now, that's why this is modeling. That's why this is an art. This is not, you're not turning a crank, people. It's about things in the world. So what do you need to do? Investigation into the world. Science. It's the only way to answer this question about how strong this argument is. It's an empirical question. The end. That's it. Now, I'm not going to tell you. It's none of my business what S is up to, so I'm not going to give you specific procedures. But you could imagine things you could do to investigate this. None of my business. I'm just a logician here. But what I've given you is a framework fully adequate to this task. This is a theory. In order to model particular situations, you're going to need particular measurements and particular information, because that's how modeling in science works. So, how do we determine this? This is the laboratory. They do a lot of fancy stuff in the lab, a lot of statistics. This is science. There's so much science that goes into this. That's a laboratory experiment. That's all kinds of shit. I'm not going to get into that. That's beneath. That's a lower level of analysis than we need at our level of abstraction to evaluate this argument. Do you understand what's happening? This is for the laboratory scientists and the pharmaceuticals and everyone else to determine. That's a scientific question. They need to answer that. And that's what goes on the box. That itself is a very difficult epistemological problem. But it ain't our problem. This is an input to our theory. You understand? It's not for us to calculate it, it's for the scientists, the relevant scientists to calculate it. And what about this? This is also science. It's a different kind of science, but you'd be damn sure that's empirical science. You know what I'm saying? That's observation and disposition and lots of things. Who knows? It depends on S and what they've been up to. The end. There's nothing more from the point of view of inductive logic to be said. Do you understand? Inductive logic is a theory that tells you, if you give me the probabilities that are appropriate, I'll tell you how strong that argument is. Where do the probabilities come from? Generally, science. And that's how it should be. Division of intellectual labor. It's not up to the inductive logician to answer all these questions. Not our job. Doesn't mean I don't care, but see what I mean? It's a theory. The theory has models. To apply the models, you got to do the same blood and guts work you got to do whenever you're applying a theoretical model to any empirical situation. And there's no shortcuts, and logic ain't going to help you. Science is what you need to do. And that's how it should be, because that's how these things work. Does that help? That helps, because I'm not really answering your question, because the questions you're actually interested in are, tell me the story of where this comes from, and tell me the story of where this value comes from. And I want to say, hey man, that's a long story of science and statisticians and all kinds of collaboration that's going to be needed to figure those things out. I can't really tell you the full details of that story, but the story can be told. And when it is, we'll have enough information to apply our theory and provide an adequate model of the strength of this argument, I think. Does everyone understand? That's how this works. Now, this is one example, but I want to go a little further, and on Friday we're going to look at lots of other examples. But let me say one more thing. How much time do I have?
No, it's actually, I'm sorry.
Oh, I'm done. Thank you very much.